So in chapter 12, we're dealing with phases, so different types of phases, solid, liquid, gas, and the energy. Today we'll be talking about the energy involved in going from one phase to another, and how much energy that takes. So for example, if we have 20 grams of ice at negative 10 degrees Celsius, and we want to increase the temperature to 50 degrees Celsius, how much energy is required. And we're just going to recap on the different types of phase changes. So here, for example, solid, liquid, gas, on the top type, on the top of the diagram, these are endothermic phase changes. So endothermic means it requires energy. So in order to go from a solid to a liquid, you have to absorb heat. When you go from a liquid to a gas, you have to absorb heat. And again, if we remember from chapter 6, from Jenkin 1, delta H is positive when we have endothermic processes. So if we're absorbing heat, our final answer should be positive at the end. Now, sublimation is going directly from a solid to a gas, and this happens for solids that have extremely weak attractive forces. We'll talk more about those attractive forces later on in the chapter. But when you have something like carbon dioxide, which has very weak attractive forces, it can go directly from a solid to a gas when you apply heat. And so that's why if you ever handled dry ice, when you take it out of the cooler, it goes directly from solid to gas. Now on the bottom, there are exothermic processes, which means they occur when they release heat. And so, for example, when we go from a gas to a liquid, we condense. That means heat is released. And a good example of this is if you've taken a hot shower, the steam from the shower hits the cold mirror, it condenses water droplets on the mirror. And then to go from a liquid to a solid, it's also exothermic. That's where you freeze a liquid. And if you've taken an ice tray, fill it with water, put it in the freezer, the freezer removes the heat from the liquid, causing it to freeze. And so all of these processes at the bottom are exothermic, meaning delta H is negative. And so if you're doing a phase change or phase transitions where you're cooling something, the final energy will be negative. Now, deposition is going directly from a gas to a solid. This occurs, for example, if it's a very cold, moist morning, you get the deposition of water vapor onto your car or onto the grass, known as frost. And so when we're doing our phase changes, we'll be going through different melting, vaporization stages, or condensation and freezing. And so when we try to graph what's occurring during the phase change, we have heating curves and cooling curves. And so a heating curve, the characteristic is we start at a low temperature and we end at a high temperature. So that's when you know a heating curve is involved. And this is the heating curve of ethanol. It gives us the melting point of ethanol. And it gives us the boiling point of ethanol. So from that, we can graph what happens as we add heat to ethanol. Now, one thing is that melting point and freezing point are the same value. So it just depends on what state you're referring to. So we're talking about solid ethanol, we refer to it as the melting point. If we're talking about liquid ethanol, we refer to it as the freezing point. But it's the same temperature regardless. And so as you add heat to ethanol when it's below the melting point, we're in the solid phase. So at point A, it's the solid phase. So as you add heat, The solid absorbs the heat up until we get to the first phase change, which is the melting point. And so at the melting point, which is B, we go from a solid to a liquid. And notice that there's no change in temperature when you're converting from a solid to a liquid. It's at a constant temperature. And then once all the solid gets converted into liquid, it keeps on increasing in temperature. So in this region here, this slant here, this is a liquid state. So it only has one phase. And then it keeps on raising in temperature until you get to the next phase change, which is the boiling point. And so the boiling point, we go from a liquid to a gas, which is called vaporization. And so D is the vaporization phase change. And then you notice there's no change in temperature when we're actually vaporizing a liquid into a gas. And then afterwards, temperature begins to increase again because now we're in one phase, the gaseous phase. And so all heating curves are similar to this. Again, a heating curve, you start at a low temperature, go to a high temperature. On the areas where you see an increase in temperature, namely the slants of the curve, these are one phases. So one phase is present. At the plateau, two phases are present as we convert from one phase to the other. Now, opposite of a heating curve is a cooling curve. So we just take a heating curve and we flip it, we get a cooling curve again. So the characteristics of a cooling curve is you start at a high temperature and you get to a lower temperature. So in this cooling curve, at this slant here, we're in the gaseous state of this substance. So as you decrease the temperature, or excuse me, as you remove heat, the temperature decreases until you get to the first phase change, which is the boiling point in this example. And at the boiling point, we go from a gas to a liquid, which is condensation. So that's what's occurring at AB, is the condensation process. Then once all the gas gets converted into liquid, as you remove heat, the temperature decreases. So as the temperature decreases, we're in the liquid state until we get to the next phase change, which in this case would be at point C. And here we go from a liquid to a solid. And this is called freezing. So that's what's occurring at CD. And then after all the liquid has frozen into the solid, then at the slant, we're just in the solid state. So depending on whether you're calculating the heat as temperature is decreasing or calculating the heat at a phase change, there are different equations to use. And so one thing we need for these equations is to know how much heat is required to convert liquid into gas or to convert solid into liquid. And that's where we get these standard enthalpy changes. So these are tabulated values that are given in the book and also in questions that we can use to see how much energy is necessary, in this case, for 1 mole of solid to convert into 1 mole of liquid, or 1 mole of liquid to convert into 1 mole of gas. And so these terms we use are delta H of fusion, which is the amount of energy needed to melt 1 mole of solid into 1 mole of liquid, and the delta H of vaporization, which is the energy needed to convert 1 mole of liquid into 1 mole of gas. Now, the reason that the heat of vaporization is so much larger than the heat of fusion is because when you go from a liquid to a gas, you'll notice that we're breaking the attractive forces that hold the molecules together. To give an example of attractive forces, if you try to take water, you have to turn the temperature up to 100 degrees Celsius to boil water. And the reason it takes so much energy to convert water from a liquid to a gas is because the attractive forces that hold the water molecules together is very strong. Likewise, if you've ever used nail polish remover, it has a very distinct odor to it and it evaporates very quickly. That's because nail polish remover has a low boiling point, meaning that the attractive forces that hold the molecules together are not very strong. And so from the value of the delta H of vaporization and the boiling point, you can actually identify which substances have stronger attractive forces. And we'll talk about that later on in the chapter. So in books, you will find the heat of vaporization and you will find the heat of fusion for different substances. Now to find the heat of sublimation, it's just the addition of the heat of vaporization and the heat of fusion. Now on the opposite end, for the exothermic processes, here we're removing heat. So the way you find the delta H of condensation is you just take the negative of the delta H of vaporization. And to find the delta H of freezing, we just take the negative of the delta H of fusion. So you won't find heat of condensation or heat of freezing in a book. You'll have to know to take the negative of its corresponding counterpart. And so here is a little chart about the difference between heat of vaporization and heat of fusion. You'll notice in all of these that the heat of vaporization is more than the heat of fusion. And again, this is because when you're going from a liquid to a gas, you're breaking in attractive forces. And so the more energy it takes to break those attractive forces, the stronger that attractive force is. So something like argon or methane has very weak attractive forces, whereas something like benzene, ethanol, and water have very strong attractive forces. So it takes more energy to break it. Now mercury has a very strong attractive forces because mercury is a liquid metal, and metals have very strong, or the metal has very strong attraction with its atoms. Now for heat of fusion, it doesn't take as much energy as heat of vaporization because when you go from a solid to a liquid, you're just weakening the attractive forces. So it doesn't take as much energy to weaken them so that it starts to vibrate. The molecules start to vibrate a little bit. But it's when you go from a liquid to a gas that you're breaking the attractive force, so therefore it takes a lot more energy. And again, all these values are tabulated. You don't have to memorize them, but you will know how to look at them as we'll get through the chapter and note, okay, that I know ethanol has stronger attractive forces than, say, benzene because it has a higher heat of vaporization. Oop, let me go back. So one other thing I want to talk about before we look at a problem is, let me get back to the cooling curve and heating curve, is what type of equations to use at the different parts of the curve. And so on the slants, anytime you have a slant and you want to calculate the energy of that temperature change, you're going to use this equation here, which is, and it should be familiar, Q equals MC delta T. And if you remember from Gen Chem 1, of course, M is mass, delta T is temperature change, but C is the specific heat. And it's the specific heat of the particular phase you're at. So if you're in the gaseous phase, you have to use the specific heat of the gas. If you're in the liquid phase, you have to use the specific heat of the liquid. And this puts the Q in joules. I'll take your questions in just one moment. Now for the plateaus, where we have phase changes, we use a different equation. We use Q equals N times delta H. And the H is depending on the process. So it could be vaporization, fusion, elect. Now this Q is in kilojoules. So when we add up all these Qs, you need to convert the ones in joules to kilojoules, because typically we have, usually the answer is in kilojoules. So here we have a phase transition. We want to know how much the amount of heat in kilojoules is absorbed when 15.5 grams of diethyl ether, I use the abbreviation DE because it's easier to write, has a molar mass of 74.1, at 5 degrees Celsius is heated to 60 degrees Celsius. And so what we see here is we're given the specific heat of liquid diethyl ether. We're given the specific heat of gaseous diethyl ether. We're given its boiling point and the delta H of vaporization and fusion. Just to let you know that sometimes when information is given, you might not need to use all of it, but they give you everything that you need. Now for water, it's understood that people know the boiling point of water and the freezing/melting point of water. So on some questions, you'll see they won't give you that information because it's understood that water, the melting point, freezing point is 0 degrees Celsius, the boiling point is 100 degrees Celsius. So we want to know how much heat is absorbed when we have 15.5 grams of diethyl ether and we heat it from 5 degrees Celsius, or excuse me, -5, the negative sign's over here, -5 degrees Celsius to 60 degrees Celsius. So the first thing I'd like to do is draw a heating curve so we can see how many different Qs we're going to solve for. And for a heating Q, it's Q added. So initially we start at, what is it, -5. And as we're adding heat, the temperature increases until the first phase change. So the first phase change will occur at in this case, the boiling point, which is 34.6. So at 34.6, we convert the liquid into gas. So we have a plateau. Then after all the liquid gets converted into gas, so L to G, then the temperature increases until our final temperature of 60 degrees Celsius. So this is what the heating curve of this transition or this change is going to look like. Now at the slants, we're in one, excuse me, that's the wrong physical state. At the slants, we're in one physical state. So at this slant here, we're in a liquid state. And this slant here, we're in a gaseous state. And at the plateau, we're going from a liquid to a gas. And so we're going to have to calculate 3 different Qs. So we have Q1, which is in the heat going from -5 to 34.6 degrees Celsius in the liquid state. Q2 is the heat needed to vaporize 15.5 grams of liquid diethyl ether, and Q3 is how much energy is needed to raise the temperature of diethyl ether from 34.6 to 60 degrees Celsius. And so we're going to use, on the slants, we're going to use Q equals MC delta T, and on the plateau, we're going to use Q equals N times delta H. So I'm going to write them out, each one. So Q1, the mass of diethyl ether, times the specific heat in the liquid state times delta T of the liquid. So that's what Q1 is going to entitle. Now Q2 is going to be the moles of diethyl ether times delta H. And since we're going from a liquid to a gas, it's going to be vaporization. And Q3, similar to Q1, except now we're going to use the specific heat of gaseous diethyl ether and the delta T of the gas. And once we find the Q's of all of these, we'll add them up and we'll get the total Q. Now you see for Q2 we need moles. So I'm going to go over here to the side and calculate the moles of diethyl ether. And it's just mass over molar mass gives us moles. You know, 3 or 4 significant figures is sufficient for it. So that's moles diethyl ether. So now we can start setting up our equations. So for Q1, and remember for Q1 it's the specific heat of the liquid and the delta T of the liquid. So remember it's final minus initial. Now for Q2, it's the number of moles times the delta H of vaporization. And Q3 is similar to Q1, except now we use the specific heat of the vapor and the temperature change of the vapor. So a very common mistake is students will use the temperature change of the entire phase transition. So now we're ready to, as they say, plug and chug. So let me go through and calculate all of these. Okay. Oops. Got it. X-axis is Q added. Y-axis is temperature. So Now we have all three Q's. You'll notice that Q1 and Q3 are in joules, so we've got to convert them to kilojoules. Because when you add them, you have to make sure they're in the right unit. And now to find Q total, we just simply add up all three Q's. And again, the final answer, you can round to 3 or 4 significant figures. It's not a big, I'm not too stickler on sig figs. Let me double check my work. And so the final answer, it takes 8.12 kilojoules of energy to take 15.5 grams of diethyl ether at -5 and heat it to 60 degrees Celsius. So on the previous example, we looked at a heating process. Here we want to know how much heat is released when 120 grams of acetone, and I give the abbreviation ACE just to make it easier for writing all the different abbreviations for all the different information. Gives us the molar mass, and it says if we cool it, how much heat's released at 75, if it's at 75 degrees Celsius, it's cooled to 10 degrees Celsius. And again, it gives us the specific heat of the liquid acetone, gaseous acetone. Here it gives us the boiling point and melting point, and of course, heat of vaporization and heat of fusion. So first thing I'm going to do is I'm going to draw my heating curve. On the y-axis is temperature. Now, since it's a cooling curve, actually we're drawing a cooling curve, not a heating curve. Since it's a cooling curve, we use for the x-axis is Q removed, because we're removing heat. Or you could just put negative Q2 if you wanted to, but either way. So now if we draw our curve, our initial temperature is 75 degrees Celsius. 75 is above the boiling point, so that tells you that we're starting in the gaseous state. So as we decrease the temperature, or excuse me, as we remove heat, the temperature decreases until the first phase change, which will be at 56 degrees Celsius. So at 56 degrees Celsius, we go through a phase change, we convert the gas into the liquid. So we condense the gas. Once all the gas is converted into liquid, then the temperature decreases again as we remove heat to our final temperature, which is 10 degrees Celsius. And you'll notice that 10 degrees Celsius is above the melting point. So that tells us that we're going to be remaining in the liquid state. So from 75 to 56 degrees Celsius, we're in the gaseous state. From 56 to 10 degrees Celsius, we're in the liquid state. So we're going to have 1, 2, 3 Qs. Now we're going to need the moles of acetone, so what I'm going to do over here to the side is just quickly calculate the moles of acetone. Get 2.066. So now Q1, we're in the gaseous state. So we're going to use the mass of acetone. Since we're in the gaseous state, we're going to use the specific heat of the gaseous form of acetone. Now here, we got to look at delta T. Now delta T is always T final minus T initial. So here it's going to be 56 minus 75. Now we look at Q2. Q2, we're going through the process of condensation. So we need to know the delta H at condensation for our substance. And so what we do to find the delta H of condensation is we just make the delta H of vaporization negative. So it's going to be 2.066 times negative 31.3. Again, we make it negative because that's the delta H of condensation. And Q3 will be similar to Q1, except now we're in the liquid state. So we use the specific heat of the liquid and the temperature change of the liquid. And again, it's final minus initial. So now we have them all set up, we can do our calculations. Oh, and that was in joules. Okay. So now again, you'll notice that the ones that we use Q equals MC delta T, they're in joules. We want to convert them to kilojoules. We can calculate Q total. So let me double check my work. So the amount of heat that's released is negative 79.53 kilojoules. One thing to notice is whenever you have a series of phase changes or phase transition that goes through the liquid gas state or gaseous liquid state, that's always going to be the one that's typically going to have the most energy associated with it, because that's where you're either breaking or reforming the attractive forces. So